Good afternoon, everyone. We are N.O.V.A.S, which stands for Nursing and Outpatient Video Access System, and we are sponsored by N.O.V.A.S Health Institute. And my name is Jonathan.
I'm Aaron.
I'm Howard.
I'm Ben.
I'm Malik.
And then Faisal.
David.
Okay, so what is our problem? Are healthcare costs increasing for senior citizens? Can we avoid unnecessary visits to a healthcare facility and save money? Well, in today's society, the population of seniors is increasing at a growing rate, or a very fast rate. So we want to help minimize healthcare costs, and minimize hospital visits. And now we're going to introduce you our product as on the screen. So the solution to our problem is N.O.V.A.S screen. So it's a two-way non-contact video link between the home-based senior and the nurse practitioner. And we are going to minimize, and it's going to help minimize healthcare costs and limit frequent hospital visits. And as well as seniors will have the opportunity to have basic care at the comfort of their home, while being able to have a human connection with the nurse. And monitoring and follow-up appointments will no longer be required at a facility. And on the bottom left, we have a picture of our product, the N.O.V.A.S screen. And the picture on the bottom right shows like the nurses and the nurses side of the video link. And he or she will be able to communicate with the home-based senior via PC, notepad, or laptop, or similar device. And then now I'll hand it off to Aaron to talk about vision and constraints.
So to achieve this within our client's constraints, we needed to decide all the different features that our device would have. So we decided it would have to have a custom video call program with a minimal user interface. Skype programs like that are too complex for our target demographic. They're relatively simple for young, tech-savvy people, but for a homebound senior, it's not easy to dial someone whenever you need to. So it needs to be as easy to use as possible. One of the requirements was that the N.O.V.A.S screen would be a touchless interface. The senior would be able to interact with the device without having to get up out of their chair and touch it. So we decided to use a gesture sensor to implement that feature. The device needs to be battery powered in case of power outage or being moved or coming unplugged. It needs to be able to have a wireless video and audio link, so we're going to be using Wi-Fi to transmit the data. And the application that we created needs to be able to start immediately when the device is powered on, so it has a seamless use for the senior. Now, Waleed will explain some of the software.
So for the software part of our project, we use an open source application called N.O.V.A.S. And N.O.V.A.S is a video calling application that works on iOS, Androids, and it can also be accessed using any laptops. So for the users to use N.O.V.A.S, they should have N.O.V.A. accounts, so that the user, when they decide to call someone, they're not actually calling the phone numbers, they're calling the registered N.O.V.A. accounts. And for our project, we modified the Android version of the source code so that we have 4 different pictures, and each picture is assigned to one registered N.O.V.A. account. So, and since our project is gestures only, so we use gesture sensor to control the software, so that when the user wants to make like a video call or to choose which contact to call, the sensor will send specific data to the Android application, and depending on the data that the application will receive, the application will do a specific thing. And now Faisal will explain everything in detail with a video.
Yeah, N.O.V.A.S screen is controlled by hand gesture only. And so the user will be able to choose their contact by waving right to left or left to right. And as you can see the video, this is how it's working, the screen with the sensor. And for making calls, the user should wait up and up vehicles, the caller should use the phone application and a registered account to call the N.O.V.A.S screen account, and by waving up, the call is received, and by waving down, the call is rejected. And if the sound wasn't clear enough, the user should be able to adjust the volume by waving right or left during the call only. And this is our software setup. And now I pass it to John to talk about it.
Okay, so here is a block diagram of our design. And the big gray box in the middle is our microcontroller, which is the quad. And it's a 6-ARM Cortex CPU. And our green boxes are our inputs. And our brownish boxes are our outputs. And at the top left, for our inputs, we have our 14-volt wall mount, which is connected to our battery charging PCB that has a 3-cell lithium-ion battery connected to it also. And on the top right, we have our infrared sensor. And on the bottom right, we have our camera. And on the bottom, we have our analog microphone. And for our inputs, on our right, we have our LCD monitor. And on the bottom left, we have our stereo capacity amplifier speakers. And then now we're going to go into detail of each of these components.
As you can tell from the previous slide, Voodoo Quad is the beating heart of the N.O.V.A.S screen. It provides the N.O.V.A.S screen with many crucial features, including but not limited to built-in Wi-Fi, LVDS output, analog audio input, I2C input, and camera connection. However, the main reason we chose Voodoo Quad was its ability to receive, compress, and transmit high-definition video quickly without loss of resolution. This is due in part to its two powerful processors. The gesture sensor that we chose to interpret the user's commands is the APDS 9960. This powerful little sensor is made up of an IR infrared LED and 4 infrared photo transistors that are facing different directions. To issue a command, the user swipes their hand over the sensor. By doing this, light emitted from the LED is reflected off the hand and hits the four photo transistors that will elicit electrical response. Since they are in a different orientation place, they each have a different electrical response. The sensor uses this to interpret the gesture. The sensor is most accurate when the hand is 1 to 4 inches above the sensor, but its maximum range is up to 8 inches. The camera we chose is the MIPL 5 megapixel Voodoo camera. This camera can do 1080p at 30 frames per second. We found this to be adequate for video conferencing, and it still doesn't overload our processors. It also comes with features like full field of view, which increases the camera sensitivity and increases signal noise ratio. I will pass it to Ben for audio.
In order for this device to work, the senior has to be able to hear and be heard. To this end, we've implemented an audio input device that consists of a microphone and an amplification circuit. The microphone chosen was a MEMS technology microphone, as it has a very, very small footprint and will be easy to implement into our project. The amplification circuit consists of a single operational amplifier, and the gain of the circuit can be set using the feedback resistor to adjust the gain of the microphone to an optimal level while avoiding feedback. The audio output consists of 2 Class D power amp chips in order to provide stereo operation. Class D topology was chosen as these devices draw very, very little current when they are in standby. They're highly, highly efficient, and they also have a very small footprint. They're powered directly off of the Voodoo via the 5-volt rail, and they power 2 8-ohm 2-watt speakers. The gain of this circuit was chosen to match the audio output of the Voodoo which was measured at about 600 millivolts. So we set the gain and sensitivity of the circuit to match that. We ended up with a sensitivity of about 628 millivolts. And the output that we managed to achieve per channel was 1.64 watts. Now I'll hand it off to Nathan to talk about power requirements.
In the design of the N.O.V.A.S screen, we're going to take into consideration patient safety as well as emergency situations. And on a day-to-day basis, the N.O.V.A.S screen is to be powered with a 14-volt AC wall adapter. And just in case the cord is disconnected or there's a blackout, we've implemented an intelligent switch mode power supply. This highly integrated battery charging IC is capable of current and heat sensing for charge termination, and even has a safety timer to avoid overcharge. The battery management system charges 3 lithium-ion cells until they reach about 11.8 volts, and when the current being drawn by the battery drops below a certain threshold, the circuit knows when to terminate charging. When the main power is disconnected, the IC switches to battery mode to supply the load, and this is done without interruption, so the call is not dropped or anything like that. And our 3 lithium-ion cells are highly compact and have a total capacity of 2,600 milliamp hours, and this gives us a minimum battery life of about 1.5 hours upon disconnection. And after testing the device, we concluded that the N.O.V.A.S screen will consume between 1 and 1.7 amps at max. And at 14 volts, this equals about 24 watts. And in the table, you can see the individual power consumption of each component listed. Now we'll pass it to Cameron so he can talk about the 3D model.
Using SolidWorks, we designed and made a case for our device. We divided our design into 3 main parts: the front cover and the back cover and the electronic sheets. The total dimension of this case is 404 millimeter by 298 millimeter, and the total thickness is 50 millimeter. This case is housing a 15.6 inch screen, as we can see here. In the front cover, we designed some holes for the camera, the gesture sensor, the microphone, and the speakers. On the top side of this case, we have some holes for cooling purposes. On the back side of this case, we have we designed some wall mounts to place the device on any vertical object, and designed some holes to attach the back cover with the front cover. Inside this case, we have our electronic sheet. This sheet will house the audio we're using, the PCB, the battery, and the battery management system. Also, we've designed some mounts to attach the speakers and the camera to the front cover. Also to attach the back cover with the front cover. Now, we're going to talk about the administration of our product.
The budget for this project was $1,000, granted to us generously by the West Health Institute. We divided this budget up into sections with the largest amount of money being spent on peripherals and parts, which included our sensors and our battery and other components like that. The main boards themselves were divided into their own section, which consisted of 25% of our budget. And we also had a portion of the budget dedicated to research and testing, which included us ordering things like development boards and other testing fixtures. We also had set aside some of our budget for manufacturing costs, including things like screws and other mounting hardware, as well as a small section of the budget for miscellaneous costs that may come up, such as parts breaking that need to be replaced at the last minute. Now, Aaron will talk to you about our milestones.
So we broke our project plan into 3 main sections, 3 main phases: design, build, and test. The design phase lasted 5 weeks, where we developed our concept and selected our hardware and came up with some user interface ideas. The build phase lasted 4 weeks, where we assembled everything and got some 3D prints downstairs and got everything together. And the test phase lasted 3 weeks, which included a week and a half of testing the UI with strangers, which gave some pretty interesting results. We completed each phase on schedule, and I wanted to say special thanks to the West Health Institute, particularly Hugh Molesworth, and SDSU alumni Michael and Patrick, and the staff at San Diego State, John, Mark, Mike, Dr. Tamala, and staff at Udu, Emmanuel, and 2 other people who helped us out, Hussein and Amanda. So thank you very much to everyone, and thank you for coming.